Hi, y'all. Welcome back to another round of physics. And yeah, let's get at it. As promised, I said we should probably work on some inductors and circuits. And so we're just going to go through and remind ourselves about Kirchhoff's voltage laws and current laws with a new circuit element. So, as previously described, how we represent inductors in a circuit is the loop-de-loop wire. Okay. Something like that. And that should remind you, be reminiscent of a solenoid, so an inductor L. And so I guess we just start walking our way through. Let's get an idea about what happens if we take a battery of voltage V and we hook it into a series circuit involving an inductor and a resistor. So we'll say an inductor L, a resistor R. And what does this actually look like when we get the differential equation and go through and solve? So go ahead, take a couple minutes, remind yourselves Kirchhoff's voltage law, Kirchhoff's current law, and go ahead and write down the equation describing this circuit. Okay, you got it? Well, let's go through. Usually, how I recommend choosing a direction for the current. Well, since we only have a single battery, that will make life a lot easier to figure out the direction there. So I'll put that current in. And then I encourage you to go through and label the high and low sides of all these circuit elements. Now, the next thing is, is that we have to identify the number of unknowns. And that is 1. We just have a single current, so that one's fairly straightforward. And so we need to write down one equation describing the circuit. Obviously, we have no junction, so Kirchhoff's current law won't be any advantage. And so we're left with applying KVL. So let's go ahead. We'll start walking around our circuit. Okay. And I'll start at this upper left-hand corner. And we start walking, and we get, I'll put drops, V drops equal V jumps. So I'll call the left side my drops. So I start walking around, and I get the drop across the inductor plus the drop across the resistor. Keep walking, and then I get a jump, the battery. Now let's go ahead and substitute in the expressions representing the drops across the inductor, then the resistor. Ohm's law for the resistor, V equals IR, so our current I times the resistance R. The battery, that doesn't change, that we just leave there. And for the inductor, you recall that we had the expression from last lecture that we define an inductance L such that the drop across the inductor can be written like this, di dt. We're done. Well, okay, we still have to, what we notice here is that we have what we would call a first order. First order because we only have a single derivative, not 2 derivatives, 3 derivatives, yada, yada, yada. First order, linear because we don't have i's or I squareds or, that kind of thing. And then inhomogeneous, genius. That's because of this battery term. Okay. And then differential equation. So we have a first order linear inhomogeneous differential equation. Now that might sound daunting, but rest assured we have already solved a first order linear inhomogeneous differential equation. See, when we do that, we did that for the case of a charging capacitor. Here, incidentally, this is called the charging inductor. So we've already done this for the charging capacitor. If we go back and look at that discussion, what we had there was this situation. And if we go through and do the exact same things, Kirchhoff's current law and voltage law and labeling the highs and lows and the direction of the current, we should have gotten something that said VC plus VR equals VBAT. We go through and substitute in the definitions, and we get something that says the charge on the capacitor divided by the capacitance plus, and here I'll use Ohm's law, but I'll be very careful. I'll say the dq dt. Okay, so I'm substituting that term in for the current times R equals V battery. So we've actually already solved this, except the one difference being instead of the final solution being a function of time describing the charge, here when we solve this differential equation, we are going to get a function of current as a function of time. There we go. You want to go through it? I assume you said yes. So let's go through. Let's remind ourselves, how did we solve that differential equation? So I'll put di dt plus IR equals V battery. Now, there are various ways to take a stab at differential equations, first order inhomogeneous differential equations. The fact of the matter is that because this is a constant, I think the easiest approach is to take a time derivative of both sides. So what I will do is take a time derivative of both sides. And so now I have di dt times R, and then I have 0 on the right-hand side. Okay. So when I solve this inhomogeneous linear differential equation, I will get a solution for what di dt is. And then I'll have to integrate with respect to time to get what I is. Okay. So it's kind of like I'm, if you will, I could rewrite this. I could say it's d dt of this new variable that I'm calling di dt plus R times di dt. So I'm kind of solving for this new variable now. New, put it in quotes. Good? Okay. Incidentally, just to let you know, and you'll see this in your mechanics classes moving forward, sometimes your E&M classes as well, but you'll see this notation. A time derivative will sometimes be written not as this, because we're lazy. It'll be written as this. Or a spatial derivative, because we are lazy, will sometimes be written as this. I think this spatial derivative notation you're probably familiar with. They introduced that in calculus. But this dot notation you might be less familiar with. To give you another example of that, rather than writing the acceleration as being d squared x dt squared, you will sometimes, more often than not in advanced text, see it simply written as x double dot, 2 time derivatives. So that's just a little notation issue for you. Okay. So this equation, if you don't like this, you could write it as d dt of I dot plus R I dot equals 0. Now, I told you when we saw these equations for the first time, anytime you have a first order linear homogeneous differential equation, that equation is separable. In other words, I can get the t's on one side and the variable on the other. So go ahead, do that for with this equation. Got it? Good. Okay. So I'll walk you through it as well. So let's go ahead. We have L di dot dt plus, oh, excuse me, let's move the I to the other side. So we'll say negative R I dot. And now we'll go ahead and get the I dots on one side and the t on the other. So we have di dot dt equals negative R over L dt. Excuse me, I said dt. That's not what I want. I want I dot. So I'm moving the I dot to the denominator, the dt to the numerator. And now we integrate. So over here, I get ln of I dot. And since I have an indefinite integral, what I'll do is I'll just say R over L times t plus some constant c. Okay. Well, we know how to get rid of that logarithm, or excuse me, that natural log. Go to another page. We know how to get rid of this natural log that we have here. R over L t plus c. We'll go ahead and raise both sides to the natural number, e. Okay. Now this right-hand side, I have it as e to the negative r over lt plus c. I'll go ahead and rewrite that. I'll write it as e to the negative r over lt times e to the positive c. And remember, e itself is a constant. So if I take a constant and raise it to a constant, this whole term here is still just a constant. So I'll rewrite this. I'll just call this constant. I'll call it a, if you will. Okay. So over here on the left-hand side, I now have I dot. Okay. And on the right-hand side, I have something that says it's some constant, e to the negative r over L times t. Okay. And already, this should start looking kind of familiar. In fact, let me ask you a different question. Okay. What do you think the units of L over R is? Units, plural, singular. Okay. What's the unit of L over R? You see it? Yeah, hopefully. You notice that right here in the exponent, it has to be unitless. R times L, R divided by L times T. This whole thing needs to be unitless. That means that the units of L over R must be equal to seconds. So that when you take L over time and divide it by L over R, you get unitless. Okay. Well, let's finish off what we were dealing with now. We had I dot is equal to some constant, which I just called A, times e to the negative RT over L, if you will. Well, now we're home free. Almost. We want the current, right? di dt. That's what I dot represents. And we really want to know the value of I. So we better e to the negative r over L times t. We better do another integration. So we have the integral of di equals a, some constant, the integral of negative r over L t dt. And okay, well, at the end of the day, we get something that says I is equal to, well, we have to do the integral here, a, and I'll put a negative L over R, e to the negative R over L t. Right? And because we had the indefinite integral, we have to add a constant, an integration constant out. Okay, good so far? Yeah. Let's go ahead and apply some boundary conditions. Boundary conditions to find what the constants A and B are. Okay. That's the technical term. The other way to think of it is essentially when you're doing it this way, you're applying the limits of integration. So either way. So if we go back and think about this uncharged inductor, last video we gave an argument that said the moment that the switch is closed and current begins to flow, okay, current wants to flow, maybe I should say, from the battery, the inductor is going to have a very large induced current. So large, in fact, that momentarily the drop across the inductor equals the drop across the battery. In other words, the total current flowing through the loop is 0. So let's go ahead and put that in. Let's use that idea. At time equals 0, the total current is equal to 0. Okay. Well, right away, that gives us a value of what B should be. If I plug 0 in here, and I get negative L over R A plus B. Okay, well, that means that the constant B must equal L over R times A. It's kind of boring, but okay, it works. So now we have something that says our current is equal to, and I'll go ahead and pull that L over R and A out. We have L over R times A, quantity 1. Now I have the negative sign here, so we got to be careful. 1 minus e to the negative R over L times T. Well, what's a second condition? Let's go ahead and look at the limiting behavior as t goes to infinity. As t goes to infinity, I should be some constant value. And in fact, I should go further than that. If I is constant, that means the potential drop across the inductor is 0, which means the potential drop across the resistor equals the potential drop across the battery. Okay. Which means we can use Ohm's law here, right here. At time equals 0, the current flowing, or excuse me, at time equals infinity, the current flowing through the circuit should simply be the potential of the battery divided by R. So let's go ahead and put that into our equation. Okay. So I'll rewrite the equation here. Greg's writing big today. 1 minus e to the negative RT over L. Okay. We'll put in time equals infinity. That means that this term should go to 0. And at the same time, our current should therefore be the potential of the battery divided by the resistance. That should equal L over R times A. Right, this term goes to 0. So what we have is that the value of the battery divided by the inductor is equal to that constant A. So at the end of the day, what do we have? We have the current is equal to L over R times that quantity V battery over L. So we see that some of the stuff is going to cancel again. 1 minus e to the negative RT divided by L. Oh, goody goody. This cancels that. And that should make some sense. What's the units of a potential divided by a resistor? That is units of current. We have 1 minus unitless minus another unitless quantity. And there we go. We now have an equation for the charging inductor. And note, okay, this looks, again, I'll highlight the similarities. This looks a lot like the equation that we would have had for a charging capacitor. Okay. We would have had, excuse me, a lot like a charging capacitor. We would have had something like 1 minus e to the negative t over RC. And out front, we would have had something like C times V bat. Okay. So a lot of what I want to emphasize here is a lot of the approaches that we use to analyze RC circuits, we can use the same approaches to analyze RL circuits. And by the same approaches, I mean we can apply KVL. We can go through and solve the differential equations in the same manner. Good. Okay, let's do one more example, and then I'll turn you loose for you to kind of ponder the other ones, okay? And practice some other ones. Okay, let's try a different example, and one that we have not had any analogies to. Okay? So here's the situation. Let us pretend that I have a battery. Okay? And what I am going to do, I'm going to actually have a double pole switch. Double pole switch, what that means is I can connect it one way and then I can throw the switch over to a different connection. Okay. So what I'm going to do is, let's say for a second that I have this arrangement, a battery, and then I have it hooked up to a capacitor C. And then what I'm going to do, I'm going to charge up the capacitor, and then I'm going to throw the switch. So I charge up the capacitor to some potential. You know it's going to be the same as the potential across the battery. Okay. Then what I'm going to do is I'm going to throw the switch to the inductor. And the question I have, the thing I would like to know, is what does the current as a function of time look like after switch is thrown? Okay. So let's go ahead. I'll simplify the circuit here. We're going to say what we're really dealing with is something like this. This is after the switch is thrown. What we're dealing with is something like this, where we have an initial potential difference across the capacitor. And of course, we'll say that we know the inductor. So let's go ahead. We'll pick a direction for our current. Namely, if this is how we charged up the capacitor, this must be the positive charged plate and the negative. And so for this situation where the capacitor is the source, okay, our current is going to flow this way. Call that I. Well, now that I have that, let's go ahead and label the high and low sides. So I've already got it for the capacitor. High side, low side. This would be the high side and the low side. And you're probably already ahead of me. Go ahead. Apply Kirchhoff's voltage law. We have that the drop across the inductor must equal the jump across the capacitor. Okay, now here's where we have to be careful. Remember that we have the charge of the capacitor, which I will call Q. And every time some current leaves, the capacitor decreases by a small amount. Okay. So if I think of Q capacitor as being the initial charge stored on the capacitor minus the amount of charge that has left, then when I take a time derivative of this, okay, so the charge of the capacitor as a function of time is equal to, and right here's the money ball, I'll say negative dq dt. Okay. In other words, the current running through the circuit is given by the negative change of the charge on the capacitor. Okay. So let's go ahead. Now I have this expression giving me the current running through the loop, the circuit, in terms of the capacitor charge. So I'll go ahead and write down my definition. We have the potential drop across the inductor is di dt. And we have the potential drop across the capacitor is given by QC divided by the capacitance. Okay. Oh, good. Okay. Well, so I'm going to substitute in this idea, this relationship between the current through the circuit and the charge on the capacitor. And I have something that says negative d squared QC divided by dt, the second derivative, equals QC over C. It's an ugly Q. Let me go ahead and get everything on one side. And so what I have is something that says the second time derivative plus, and I'll put 1 over LC here, times the charge on the capacitor is equal to 0. What we have here is a second order linear homogeneous differential equation. A second order linear homogeneous differential equation. And what I will say is that a second order linear homogeneous differential equation will always have two solutions. Generally, how you prove this is what's called the characteristic equation. I believe it's characteristic equation. Now let's look at this for a second, though. Yes, it's a second order linear homogeneous differential equation. Okay. A perfectly valid method for this, rather than doing the characteristic equation, a perfectly valid method is simply guess and check. I know that seems somewhat unsatisfying, but that is technically a perfectly valid mathematical process. I think this is the solution. I'll plug it in and show that it works. Okay. Let's look at this equation for a second. Oh, excuse me. let's look at this equation for a second. We have dc dt plus 1 over LC QC equals 0. Let me ask you this. Can you think of a function that when you take two derivatives, so can you think of a function so that when you take two derivatives, you end up with the same function with a negative sign? Can you think of a function, that's QC, so that when you take two time derivatives, you end up with the same function with a negative sign? You say, yeah, I know a function. Try it. Check. Sine of t. Okay. If I take a derivative of sine of t, d dt, I get cosine. Oh, excuse me. I should write this out properly. If I take that, I get a cosine of t. And when I take two derivatives, I end up with the same function with an additional negative sign. Or if you prefer, you could also say cosine. Cosine of t will do the exact same thing. You take two derivatives, you end up with a negative cosine of t. Okay. These are our two solutions to the second order linear homogeneous differential equation. Okay. So I'll go ahead and write down the solution now. Okay. Our solution is something like this. The charge on the capacitor as a function of time is equal to, and I'll put a constant out front, constant sine of t divided by LC square rooted. And you say, well, why did you put that LC in there, that square root of LC? Don't forget, when we look at our differential equation, we have this constant term in front. Okay. So what happens is after I take two time derivatives, okay, when I take two time derivatives of sine of t, not only do I need that negative sign, but I also need that negative sign, but I also need a 1 over LC out front. Okay. Without that 1 over LC out front, then when I take the derivative and add it to the original thing, I won't necessarily get 0. Okay. So we have to include this square root of LC in there. And I'll put B cosine of t divided by LC. Cool. Right? Now let's go through. We should probably figure out, we're almost done, but we should probably figure out what the values of A and B are. And this again comes back into what we would call the boundary conditions. So let me ask you this. At time equals 0, should QC be 0 or should it be non-zero? Non-zero. Right, let's get rid of that one. At time equals 0, we're dealing with a charged capacitor, and therefore QC should be non-zero. Okay? In fact, we could go even further than that. At time equals 0, QC should be equal to the capacitance times the battery potential. Remember, we use that battery to charge things up. So let's go ahead. Let's look at our equation. And if we take our equation and put at time equals 0, we get, well, Sine of 0 is 0, so we get 0 there. Cosine of 0 is 1, so we get plus b times 1. And we know that this whole thing should be c times v bat. So that tells us what the value of b better be. Cool? Good. Good, 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 good. Okay. So we have what the value of b is. Now we've got to figure out what is this value of a. And here I'm going to use not the initial condition on the charge of the capacitor, but rather the initial condition on the current. So let's go ahead and write down the current as a function of time. Well, that's a time derivative of the above expression. And we should have something that says A times 1 over the square root of LC cosine of t over the square root of LC plus b times 1 over the square root of LC sine of t divided by LC. So we need to use a condition on the charge and the current. Take note, this is a negative b. There we go. Now we already know what the value of b is. What I'll highlight now is that at time equals 0, what should the current be running through the circuit? Keeping in mind, I have an uncharged inductor. It should be 0. Right? Remember that inductor doesn't want to see the charge start flowing. It wants to maintain the status quo. And so if we look at the second equation that we've written and plugged in time is equal to 0, we should have something that says 0, the current, equals, well here, cosine of 0 is 1. And so I end up with something that says A divided by the square root of LC minus sine of 0 is 0. So I get 0. And the only way for this to occur, and now you see it, the value of A must be equal to 0. Ah, good. So what do we have for final answer? We have that the charge on my capacitor as a function of time is written as the capacitance times the initial potential of the battery cosine of t divided by LC square rooted. We have that the current running through the loop, this is capacitor, we have that the current running through the loop is given by that constant B as in boy divided by the square root of L times C times the sine of T over LC square rooted. And I have again forgotten my negative sign. Of course, you could simplify this a little further if you want, right? You have the C divided by the square root of C. So we could rewrite this as negative C over L times the potential of the battery sine of T divided by LC. Very cool, huh? What does this mean? This means, and assuming perfect conductors and perfect wires and capacitors and everything, this means that if we take an a charged capacitor and hook it up to an inductor, the current will flow. You will decrease the energy storage in the capacitor. Current will start flowing, and what will happen is you end up charging the inductor. You transfer all of the energy stored in the capacitor, and you end up storing that energy in the inductor. Okay. Now, of course, bear in mind, this energy is stored in the magnetic field, where for the capacitor, it's stored in the electric field. Now, once the capacitor is completely depleted, no more energy stored, that is when the inductor has its maximum storage. It's fully charged, the inductor. And so then what happens? Well, the inductor starts seeing that the current stops, and it doesn't like that. So sometime later, when the capacitor is fully discharged, the inductor sees that the current has decreased and therefore will start running current the other way. It doesn't like seeing that decrease. Okay? And so what will happen is it will take its stored energy and start forcing current charge back onto the upper capacitor plate. And so the process repeats. It dumps the energy from the inductor back to the conductor. Well, once the inductor is fully discharged, the capacitor is fully charged, and so the capacitor will start running the current the other way again. And so this current sloshes back and forth between being energy stored in the inductor and energy stored in the capacitor. In fact, we could go slightly further. Let's look at this argument in the sine function. Okay? This 1 over LC square rooted. What do you think the units of that are? Or maybe I should be more specific. What are the units of LC square rooted? Probably see it already. The argument in here has to be unitless. LC must have units of seconds. Okay. Now, we don't call it the time constant, right? This isn't an exponential decay or an exponential growth. Okay. This is a sine function, okay? A periodic function, if you will. So rather than thinking about a time constant here, we usually define 1 over LC square rooted is defined as being an angular frequency. Remember, the angular frequency is 1 over seconds. And more often than not, you'll see this subscripted with a 0, and this is called the natural frequency of the circuit. 1 over the square root of LC dictates how quickly the energy is transferred back and forth between the inductor and the capacitor. Very cool, huh? Last thing, and we'll probably treat this in class on Wednesday. We'll just wait and see. Okay. Last thing is, what happens if I include a third element here? So instead of having just a capacitor and an inductor, you put the resistor in as well. You can probably get a sense of what happens. Remember, the resistor, the job of a resistor in a circuit is to withdraw energy. Okay? It's taking energy that's stored in the electric or the magnetic field and using it to do something else, heating a tea kettle or turning an engine or something like that. The purpose of a resistor is to remove energies from the circuit. So you can imagine as this charge sloshes this way, the resistor removes a little bit of the energy. Then as it sloshes back, the resistor removes a little more. And as it goes back and forth, the resistor keeps bleeding off a little bit more of that energy. Okay. So you can kind of get a sense of that. Let me say the last thing is that the amplitude is related to the energy that's being stored. Okay, we'll talk about that later. But what happens is you end up with an oscillation due to the capacitor and the inductor, but the amplitude of that oscillation continually decreases until it's gone. Okay. That's the effect of the resistor, is that you're bleeding energy off from the total circuit so that eventually there's no more current flowing. Cool, huh? Okay, I think that's enough for today. We've gone through a little bit of KVL, KCL again. We've gone through some of the basic circuits involving inductors and resistors. Of course, we could add more inductors if we want, and the same stuff holds. Okay. And we've talked briefly about the differential equation associated with the capacitor and the inductor in a circuit, this oscillatory behavior. I think that's enough for now. Thanks for your attention. I'll see you next time.